performance characteristics. So we are now going to study communication antenna performance characteristics. So this sounds complicated, but it is mostly asking how do we judge whether an antenna is good for communication. An antenna is simply good or bad. We look at several characteristics. The important ones for your muscle buds are radiation pattern, directivity, gain, beamwidth, polarization, radiation efficiency, radiation resistance, antenna impedance, bandwidth. So radiation pattern. We already studied this. How strongly does the antennas radiate in different directions? For example, the direction antenna concentrates radiation in central second directions. An isometric antenna would radiate equally in every direction. So radiation pattern tells the directional behavior of the antenna. Directivity. We already studied these two. Directivity tells us how concentrated is the radiation in a particular direction compared with an isoelectric antenna. D equals to M x by U average. Higher directivity means the antenna concentrates radiation more strongly. For example, this is low directivity, this is high directivity. The second antenna concentrates radiation strongly in one direction. So this is one antenna, this is one antenna. You can see the directions. It concentrating the radiation in one direction very strongly rather than this. So high directivity means high directivity. Also, we can observe the directivity with radiation pattern also. How concentrated is the radiation pattern in a particular direction compared with an isotopic content. This is yeah, U average means this is isotropic antennas average, and this is U max means the highest intensity of a particular radiation, particular low. Higher density directivity means antenna concept. Gain. Gain is related to directivity but includes antenna efficiency. Gain is also related to directivity. Gain tells us, we discussed earlier, what is gain. Gain tells us gain equals to neta D. Neta equals to antenna efficiency. So gain equals to directivity into efficiency. This distinction is important. Directivity means concentration of radiation. Gain is concentration after accounting for losses. So directivity tells concentration of a radiation to particular direction, where gain tells us how much the concentration was the profit, like profit or loss. Here it is gain or loss. The intensity gained by the directivity, where concentration after accounting for loss. Like antenna loss is there, right? Antenna losses some power. Antenna takes some power from the produced radiation. So that loss is it is talking about greater antenna efficiency. So it will calculated by antenna efficiency gain equals to directivity into efficiency beamwidth. This is a very important antenna characteristic. Imagine a directional antenna. Main beam the main isn't infinitely narrow. We measure its width. Actually, imagine a directional antenna. The beam isn't infinitely narrow. We measure its width. The most commonly used one is half-power beamwidth. What does half-power mean? Suppose maximum radiation power is Vmax, half of that is Vmax by 2 in decibels, 10 log 10, like in decibels, 10 log 1 by 2 base 10, approx equals minus 3.1 dB. Therefore, half power point equals to minus 3 dB. We find the two angles where the radiation falls to half of its maximum. So actually, I read about this. It is minus 3 dB means decibels. It was like 10 log 10 1 by 2. It was a way of taking the representing the power. because the power values were very big, so we represent it with dB. So here minus 3 minus 3, this is maximum, this is the angular separation between these 2 points is the half power beamwidth. So the angle separation between these two, it's separated with an angle, it is called half power beamwidth, which we call it as HPBW minus theta 2 minus theta 1. Here angles we didn't even. Suppose maximum radiation power is given, so half of that is given as PT. Beam beta 3 minus beta 1. So, when beta minus 3 dB came from, and how, like, how reduced we know radiation of low null the directivity, etc. Then what is doing? I know bandwidth for because. So don't confuse bandwidth with beamwidth. Beamwidth is different. So minus 3B comes directly F1. The underlying logic of half-hour beamwidth distributed territory is exactly the same, except instead of measuring across frequencies edges, thus measuring across angles or decreasing the space. So this is antenna, side lobes, main lobes. This is half-hour beamwidth, the angle between the main lobes, antenna gain, and this is the half-hour beamwidth. The mathematical logical of minus 3b decibel power express ratio of power, the formula to convert a power ratio into decibels is power of dB equal to L of L long 10 P measured by Pmax. When the power drops to exactly half 50% of 0.5 of its maximum peak, power dB equals 10 log 10 0.5 minus 3 dB. Therefore, minus 3 dB is just engineering shorthand for point where the power is cut off, connecting triangles to mean because of you understand frequency bandwidth, comparing the two concepts directly, directly makes the spatial logic of an antenna easy to understand. What is it measures? Frequency bandwidth, signal strength across frequencies, angle bandwidth, signal strength across physical space angles. Uh, the center, resonant frequency, the exact center of the main lobe, maximum directivity. So, and beamwidth is measured at the main lobe. The frequency bandwidth is measured at the center of resonant frequency. Here, minus 3 dB frequency where the power drops to 50% cutoff. Here in angle beamwidth, angles where power drops to 50% cutoff. So it is the intensity of the radiation pattern diagrams. The goal defines the useful range of frequencies, define the useful tone of coverage, define the useful range of frequencies, define the useful tone of coverage. So, you understand, right? This is simply actually Google is asking better than ChatGPT. If you see, it is answering better than ChatGPT. But ChatGPT is like a best charter. Polarization, we already encountered this with the dipole. Polarization describes the orientation of electric field of the radiated electromagnetic wave. Common types: linear electric field remains in one plane direction. Linear polarization. Vertical dipole generally produces a vertically polarized radiation in principal radiation direction. Circular. The electric field direction rotates as the wave travels. So this is not electromagnetic wave. This polarization tells us the electric field direction in an antenna, where for an dipole antenna, it is a linear polarization. The electric field is narrow to the along the antenna parts, but for circular polarization, antenna will be uh, direction rotates as the wave forward is constant magnitude. So electric field direction rotates in a circular antenna. In elliptical antenna, the most general case is elliptical polarization. Circular polarization is actually a special case of elliptical polarization. Radiation efficiency. Not all power supplied to an antenna becomes radiated electromagnetic energy. Some power is lost mainly as heat. Suppose P input equals to 100 watts, P radiated equals to 80 watts, then neta equals to P radiated by P input, neta equals to 80 by 100, neta equals to 0.8 equals to 80%. So radiation efficiency tells us what fraction of the input power is actually radiated. Hmm. So radiation efficiency. Not all power supplied to an antenna becomes radiated electromagnetic energy. Some power is lost, mainly as heat. We know power lost in antennas after producing an electric wave energy. Suppose P input equals to 100 watts and P radiated equals to 80 watts, then the loss is neta equals to P radiated by P input, neta equals to 80 by 100 equals to neta equals 0.8 equals to 80%. So radiated efficiency is versus the fraction of input power is actually radiated. We see this radiation efficiency here also. So antenna efficiency is the radiation efficiency. Why we need a radiation efficiency? Because power is not exactly same in the electromagnetic wave after transmitted transmitted. Some power is lost mainly as heat. Suppose the power is 100 watts and radiated is 80 watts. So we know input power, the radiated power, then it is easy to know the efficiency of the power loss. Neta equal to P rated by P. 0.80% is the efficiency of the antenna. So radiation efficiency tells what fraction of input power is actually radiated. It doesn't tell loss, it tells us the efficiency of the antenna. Hmm. Radiation, radiation resistance. This one connects directly with the half-wave dipole we studied. An antenna has a radiation resistance RR. It represents the power that is effectively carried away by electromagnetic radiation. The radiated power can be written P rad equals to I squared RMS RR. So although radiation resistance looks like an ordinary resistance, it represents radiated power, not heat loss for an ideal thin half-wave dipole. RR equals to 76 ohms. So, yes. This one that comes to half-wave dipole, radiation resistance. So you know half-wave dipole. Half-wave dipole is nothing but for a dipole. If you take the below rod and replace it with a plain sheet like glassy surface, glassy metal surface, then it acts like another rod for the dipole. It is same as it is mainly used in cars. Above cars, you will see the half-wave dipole. It is also called as monopole, I think. Monopole or half-wave dipole. It represents an antenna has a radiation power RR. It represents the power that is effectively carried away by electromagnetic radiation. The radiated power can be written as E radical choice to RMS RR. So although radiation resistance looks like an ordinary resistance, it represents the radiated power, not heat loss. So for an ideal thin half-wave dipole, RR equals to 0.2. Mm. This is radiation power. This is what is it? Radiation resistance. Also, radiation resistance looks like an ordinary resistance, but represents radiated power. So, it is a part of the radiated power, right? Radiation resistance is a part of the radiated power, not heat loss. For an ideal thin half-wave dipole, R equals to 73 ohms. So, this is not heat loss. This is the radiation voltage drop. Uh, Antenna impedance. The antenna also has an input impedance. Zn equals to R plus Jx. R is the resistive component, X is the reactive component. The resistive part can include radiation resistance and loss resistance. R equals to uh, the radiation resistance plus the radiation loss. The negative power transfer is negative or the antenna impedance to be properly matched to the transmission line. For example, if the feed line is 50 ohms, we try to make the antenna's input impedance suitably as close to 50 ohms at the operating frequency. So if the field line is 50 ohms resistance, we try to make the antenna's input impedance suitable. Like the antenna here behaves like a load, close to 50 ohms at the operating frequency. Bandwidth. An antenna doesn't necessarily work equally well at every frequency. Let me explain. Different antennas work with different frequencies. The operator manufacturer will deal with it. For example, FL equals 900 megahertz and FH equals to low frequency is 900 megahertz, low frequency is 1000 megahertz. Then bandwidth is 100 minus 900, 100 megahertz. A wideband antenna can operate extensively over a large frequency range. The big picture, you can think of antenna performance like this. How does it radiate priority to how concentrated in the radiation beam, how concentrated is it after loss, beam width, how wide is the main radiation beam, uh, polarization, what the orientation does the oscillate, electric efficiency, how much input power radiated, radiation resistance, how much power is represented as radiation, input impedance, how does the antenna electrical look at the field, bandwidth, or what frequency range does it work properly. One particularly useful relationship, remove the connection which equals to meter D, the directivity, which is efficiency driven. Here some due to efficiency, the power loss will happen. And that's essentially the communication handling of the portion completed. After this, enter maturity and filter block is essentially complete. So what's next? Oh my god, my laptop is overheating. Oh my god. Tablet level. I believe you have understood what And what's next? Waveguides. Yeah, we covered all this, and further now if we are following the full syllabus, the previous is me, I recommend you to waveguides. Anything. Waveguides is nothing but the radiation pattern itself. It represents antennas, like see, waveguides. First, the computer diagrams you might have seen on the basic question is very simple. How can we force an electromagnetic wave to travel from one place to another at a very high frequency? How can we force an electromagnetic wave to travel from one place to another at very high frequency? We already know about transmission lines. For lower frequencies, we can usually buy things like source load transmission line. But at micro frequencies, ordinary two conductors transmission lines become less convenient because the field dimensions loss regulation becomes significant, so we can use a waveguide. What is a waveguide? A waveguide basically a hollow conducting structure that guides electromagnetic waves. The most common example is rectangular metal tube. Electromagnetic wave. It looks almost like an empty metal pipe, but here's the important point. The wave is not traveling their way. The electromagnetic field exists in the space inside the conducting walls. Why does the metal wall matter? Remember what happens when an electromagnetic wave encounters a good conductor. The conductor forces the tangential electric field at the surface to satisfy the conductor boundary equations. It equals to zero. This is the directive directly connected to the boundary condition that you are already studied. So if previous topic wasn't wasted, the conductor was constant electromagnetic field. The constant allows particular field patterns to exist inside the kite. Why can't any arbitrary way travel inside? This is the important difference from a simple wire. The conductive walls impose boundary conditions. Therefore, only certain electromagnetic field conditions are allowed. They are called modes. Waveguide physical field pattern. So this waveguides will take the help of Google. Will it can explain waveguides. We were we were experimenting with Google. Waveguides or no. Next silicon waveguides or ChatGPT explanation. Imagine your help. So the waveguide is a whole of metal pipe or dielectric structure with a lower and higher. We can see in this. We waveguides are physical structures that guide electromagnetic waves from one point to another. So waveguides are not something we cannot see. It is a physical structure. There are physical structures. Wave from one point to another with minimum loss of power. So with no huge loss of power, unlike standard copper wires that carry electric currents, waveguides channel high frequency electromagnetic waves, especially in the microwave and the millimeter wave spectrum. Think of them as high SCM pipes or radio waves where the signal bounces off the inner walls instead of traveling through a wire. So wavegates are, I think, replacements of one transmission line. Here is clear structure breakdown to help you master this for telecom audio. So at the replacements of transmission lines here at the wavegates are new technology used replacement of transmission carry high frequency radio electromagnetic if transmission power loss is the problem, so we use waveguides. So waveguides are used for transmission of but we can manage power loss with the help of we know that the transmission line has a circuit elements like transmission of circuit elements. We can use an app like we have formula Z Z equals to Z naught plus Z naught plus Z naught into um, Z ZL plus Z naught um, beta tan beta tan beta um, beta L by ZL plus um, Z naught plus ZL uh, tan beta L. This is for input linear circuit. No, this is not the impedance matching. We use impedance matching. We use impedance matching to manage power loss. What is the that and what is use of waveguide? To answer your first question directly, now waveguides are not a new technology. They were invented in the late 19th century and mainly developed during World War II. We have asked an extent deeply technical question. You are completed right that we use impedance match formula Z equal to Z naught to match impedance to eliminate reflection losses. However, impedance matching only stops power from reflected back to the source. Cannot stop the two physical causes of power loss that happen inside the cable. Itself at a microwave frequency, dielectric loss and radiation. So this is not a reflected loss. It is a cable itself or the micro frequencies. We have know the coaxial cable has the in in the outer conductor and inner conductor line. In the middle is the dielectric. The dielectric has process or radiation loss happens. Here is exactly what impedance matching is the event, and why waveguides become physically mandatory at high frequencies. That's the waveguides become physically mandatory at high frequencies. Impedance, so this is a micro frequency dielectric and radiation. Use is exactly why impedance matching isn't enough. Waveguides become physically mandatory. Impedance matching uses internal power displacement. Okay, can we impedance matching ensures that 100% of power enters the transmission line, but once the power is inside a coaxial cable, it encounters two major forms of physical restriction that not circuit formula conflicts. Dielectric heating, coaxial cables require a plastic or Teflon spacer to keep the inner wire center. At gigahertz frequency or rapid alternating current forces the molecules of the plastic insulator to vibrate within a transfer frequency. This transceiver signal directly to wheel waveguides are hollow and use air eliminating this loss entirely. The skin effect. Conductor loss. As frequency rises, electric current is pushed to the area outer skin of the wire. The effective cross-sectional area of the wire shrinks to a microscopic layer, causing the cable's internal resistance to skyrocket over large inlet surface areas, minimizing the resistance. Hmm. Yeah, waves have large inlet surface areas. The cables have very internal resistance and very cross-sectional thin cross-sectional area where waves have very high large inlet surface areas, which minimizes the resistance, but the cables have internal resistance. So can we use transmission lines of circuit elements as of the law? Okay, let's we use um, waveguides. I am unable to see waveguides. Oh. Okay, waveguides. Okay. So waves are physical structures that guide electromagnetic waves from one point to another with minimal loss of power. Unlike standard copper wires that carry electric currents, waveguides channel high frequency electromagnetic waves in the microwave and millimicrowave spectrum. Think of them as high extent pipes for radio waves where the signal bounces off. Give images also to understand. These diagrams illustrate how waves travel, how feelings distribute, and why the physical structure changes reacting at high frequencies. Structural difference. Gradual cable access voltage. Your formula Zn equals to Z naught into ZL plus Z naught term because works perfectly on transmitters because they are two separate conductors, the inner and outer conductor. Waveguide is one hollow tube. So waveguide is one hollow tube. For in transmission lines, we have this inner conductor, this is outer conductor. But here, if you see, waveguides is one hollow tube, wave propagation. Like this is metal tube, sphere tube, this is a circular tube. The left image equaxial and the right image shows whole metal rectangle and circular tube. There is no inner core or no plastic. The wave travels purely through the open air or a vacuum effect, open air vacuum effect. How the wave travels inside. Because the waveguide does not have a center wire to act as a strike track, the waveguide does not have a center wire to act as a electromagnetic, we can travel central to act as a strike track. The electromagnetic wave cannot travel in a straight line. Instead, it propagates the continuously bouncing of the inner conductive walls via total internal deflection. So total internal deflection happens in this wave metal, pool of metal. So this total due to the total internal deflection, the wave bounces, and raise wave propagation. The left image is simply wave diagram shows how a wave bounces zigzag down the pipe. The right image is 3D view showing how the actual alternating electric and magnetic fields. It looks more like an horn antenna. Uh, and the magnetic field loop shape themselves dynamically as they bounce forward. Field distribution. Syllabus more. When you study waveguides in your syllabus, you will look at a field distribution plots across the cross section. The most important mode to memorize, for example, is P10 mode, which is dominant mode in rectangular waves. Um, what is the mode? How waveguides the concept of modes. Waves do not just travel straight through waveguide. The bounce of the conductor walls at specific angle. This bouncing creates distinct field patterns called modes. So the field patterns in the polo pipe is the modes. They are the modes. Waveguides cannot transmit direct current. A low frequency field, they require a minimum frequency or function to function known as cutoff frequency (FCM) signal. Along this frequency cannot propagate. Signals travel inside the waveguide in two primary configurations: transverse electric modes. The electric field is entirely perpendicular towards the direction of propagation. There is no electric field in the direction wave is traveling. The transverse magnetic modes, the magnetic field is entirely perpendicular to the direction of propagation. No transverse electromagnetic or which we call mode, where both fields are perpendicular to the direction of travel, cannot exist in whole single conductor wave guide. They require two conductors like a axle. So transverse electric mode. The electric field is entirely perpendicular to the direction of propagation. There is no electric field in the direction of wave is traveling. Hmm. What is the mode? Mode is a way of the field patterns are itself for modes. Then what is transverse electric mode? The signals travel inside a waveguide in two primary configurations. It is transverse electric, this is transverse electric modes and transverse magnetic modes. The electric field is entirely perpendicular to the direction of propagation. So propagation is where the wave is moving. Electromagnetic wave bounces, right? The bouncing propagation. The electric field is the direction is perpendicular to the direction. There is no electric field in the direction of wave is traveling. In the direction of wave parallel, there is no travel, but in perpendicular, perpendicular is perpendicular. Transverse magnetic wave. The magnetic field is entirely perpendicular to the direction of propagation. It is also called perpendicular. Dominant mode. About structure. Hollow tube with a rectangular cross, hollow tube with a circular cross. There are two types of waves, rectangular versus circular, where hollow tube with a rectangular cross section with a high section to the start. E10, a low cutoff frequency is to means its excitation is easy and with a lower cutoff frequency it works. Application standard microwave links, radar systems, couplers. Pros simple to design, stable polarization, phones harder to manufacture and sharp bends. Quality with a circuitry line, most common dominant mode. Radar antennas, long vertical feeds, rotating joints, handles high power, easier to manufacture, suffers from polarization, rotation. The wave can twist. Okay. Key mathematical formulas to memorize cutoff frequency of equals 0 to alpha. For the transverse, it you can. This is T11 is for the circular wave. For your exams, you will frequently need to calculate these three parameters for rectangular waves. First is cutoff frequency, is 0 to alpha, where C is shape of light, speed of light, and A is the wider inner dimension of the waveguide. Guide wavelength lambda g, the wavelength of the signal inside the waveguide, which is always longer than the wavelength in free space. Lambda is equals to lambda naught by root over 1 minus lambda naught by q a whole square. Wave impedance, Z equals meter by root over 1 minus fc by f whole square, where n is the anesthetic impedance of the space, roughly 377 ohms, and f is the operating frequency. To help us dive deeper into the syllabus, let me now visualize to practice a few numerical problems involving cutoff frequency and rate. So we'll stop this waveguide here. We understand what is waveguide. If you want, we'll come again less. My brain is building a tension now. What's next? I completed waveguide, understood it, what are modes, where answers, For my exams, if they ask more theory like this, logical theory, I will score more. If they ask problems, I will be thinking the formula and stuck there. What is the formula? Like for Thevenin's theorem, if they ask how do you solve it, Thevenin's theorem we replace a whole circuit with a equivalent voltage source and a resistance. We call it V thevenin and R thevenin. How does we do it? I forget. How do we do it? First we calculate what we do. Yeah, yeah. We have for a circuit we have A and B. We have two open. We calculate. We use some KVL across there, and then we first calculate equivalent yeah, resistance by ignoring the open resistor components. We call it normal resistance, and we solve the what we do. We solve the uh, we use KVL to calculate VThevenin, and then we calculate RThevenin using and so we got resistance, right? We got resistance, and we'll calculate between A to B. We calculate the two at the A node and B node. We calculate the voltages, and we using KVL. Then we take the difference and we get A to B uh, drop voltage drop, which is it is called VThevenin. Then we need to calculate RThevenin. How we will calculate? The we will take what? We will take the um, yeah, actually I have one idea. Here we can A to B we can fix some one voltage energy one voltage battery or the understanding way and calculate the whole circuits like that, or we should calculate the whole circuit side and leave for very confusing. Okay, what's next? A computer gets an amount transfer cycle, transfer, transfer magnetic. Words. But why transfer circuit? Both are same. Mm, mm, mm. So, two configurations of magnetic field. Like the configurations inside, we have both configurations, but we separated them as TE and TM. TEM, fully we call it as TEM, transverse orthonormative modes, where both fields are perpendicular to the propagation wave, cannot exist in a hollow single conductor wave with the coequivalency like a coaxial cable, where both fields are perpendicular in the direction of travel, cannot exist in a hollow Single conductor waveguide, they require two conductors like a coaxial pair. What? EM wave is electrofilling in must be completely flat. The answer against the direction of the wave. Imagine pushing a cardboard sheet down in halfway. The electrical lines must start on the surface and end on anchor. The magnetism must start from complete third unbroken edge. Why a coaxial cable can carry TM. He's not talking about the cable, we're talking about fluid. Also can carry a TM wave. The wave is just one single hole in metal pipe. There is no inner wall. To try to force a TM wave into it, the lots of weight will take down due to the roof. The electrical lines cannot just float in mid they must start and end on a conductor. If you have only one outer or metal cell, an electrical line starting at the top wall, you would have to look back and enter the bottom one. To do that, the line has to run forward or back. The movement it pins forward, which is no longer flat transfers the magnetic field. Ampere's law, magnetic fields must form closed loops according to the Ampere's law. The magnetic field loop cannot exist in empty space unless there is a physical current flowing right through the center of the loop. Since a wire is solid, there is no central carrying current. Therefore, a magnetic loop cannot sit flat in the cross section. The loops are forced to tilt forward and stretch along the length of the pipe. Because the fields are forced to bend and tilt forward along the pipe, they can no longer be fully tensile. The result in a coaxial cable, two conductors can travel down the fluid plate hole. Then a wave waves are forced to bounce zigzag walls, creating a TV or TMS where one of the field is always tilted forward in the direction of rocket. So TM we will want for coaxial cable, not connectors we call TM and the TV. But for the waveguides we call TM and TV. Mhm. C equals to 2 by alpha, 2 by A, EC, EC by A, F equals to 2C by A, C equals to 3 dot light. So one thing, ಎಷ್ಟು ಫೋನ್ చేశారు కదా I want to share is ఫోన్ చేశారు కదా so my brain ఎందుకు ఫోన్ చేశారు అడుగుదాం so I think when I'm thinking that without my brain works very good like I remember the formula very nicely uh, I don't understand why you're talking to um, so I'm open-minded I will tell anything that comes to my mind yes some